students, let us start with theorem. Composition of two uniformly continuous function is continuous. Okay. Proof. Let f from xd to y row and g from y row to z sigma be uniformly continuous function. Here our claim is we have to prove composition of two uniformly continuous function is continuous. Here we have taken f is a function from xd to y row and g is a function from y row to z sigma. Both are uniformly continuous function. Our claim is G composite f means composition of f and g is uniformly continuous, and G composite f is a function from xd to z sigma is uniformly continuous. That is to show that for given epsilon greater than 0 there exists delta greater than 0 such that sigma of G composite f of x1 comma G composite f of x2 is strictly less than epsilon whenever d of x1 comma x2 is strictly less than delta, and x1 and x2 are belongs to capital X. Okay. Here fix epsilon greater than 0. Since we have here our assumption is G from y row to z sigma is uniformly continuous function. Since G from y row to z sigma is uniformly continuous function. Therefore, by definition of uniformly continuous function, for given epsilon greater than 0, there exists n greater than 0 such that sigma of g of y1 comma g of y2 is strictly less than epsilon whenever row of y1 comma y2 is strictly less than n, and this y1 and y2 are belongs to capital Y. Okay. Again, f from xd to y row is uniformly continuous function. Again, by definition of uniformly continuous function, for eta greater than 0 there exists delta greater than 0 such that rho of f of x1 comma f of x2. Why rho of f of x1 comma f of x2? Rho of f of x1 comma f of x2 is strictly less than eta for d of x1 comma x2 is strictly less than delta. Here whenever, and x1 comma x2 is belongs to capital X. Okay. Call this is equation number 1. This is equation number 2. Now f of x1 is equal to y1. Why? Because our function is from x to y. X1 and x2 are belongs to capital X, and y1 and y2 are belongs to capital Y. So f of x1 is equal to y1 and f of x2 is equals to y2. Okay. y1 comma y2 belongs to capital Y. Okay. Therefore, this equation becomes rho of f of x1 is y1 comma f of x2 is y2 is strictly less than eta whenever d of x1 comma x2 is strictly less than delta. This x1 and x2 are belongs to capital X. Okay. Suppose this is equation number 3. Therefore, from 1, 2 and 3, therefore from 1, 2 and 3, for epsilon greater than 0, there exists delta greater than 0, such that sigma of g of y1 is f of x1 comma g of f of x2 is strictly less than epsilon whenever d of x1 comma x2 is strictly less than delta. This x1 and x2 are belongs to capital X. Okay. So this is equivalent to sigma of g composite f of x1 comma g composite of x2 is strictly less than epsilon whenever d of x1 comma x2 is strictly less than delta. x1 comma x2 is belongs to capital X. Okay. That implies g composite f is a function from xt to z sigma is uniformly continuous. Hence, we can say that composition of two uniformly continuous functions is continuous. Composition of two uniformly continuous function is continuous. Hence, proof of theorem is completed. Let us take one more theorem. Let and y row be metric spaces. Let x3 and y row be metric spaces and f from x to y be a uniformly continuous function. If sequence xn is a Cauchy sequence in capital X, then sequence f of xn is a Cauchy sequence in Y. Okay. See here, what is theorem say? Let x3 and y row be two metric spaces. F is a function from x to y. Be a uniformly continuous function. If sequence xn is Cauchy in X, then we have to show that its image is Cauchy sequence in Y. Okay. In theorem, we have given that f is uniformly continuous function. F is uniformly continuous function. Therefore, by definition of uniformly continuous function, for a given epsilon greater than 0, there exists a delta greater 0 such that d of x comma x dash, we may take x1 comma x2, it doesn't matter, strictly less than delta for x comma x dash it belongs to capital X, that implies row of f of x comma f of x dash. Okay, we may write this also, row of f of x comma f of x dash is strictly less than epsilon whenever d of x comma x dash is strictly less than delta. Okay, in particular we have d of xn comma xn is strictly less than delta for all n comma m is greater than or equal to is strictly less than delta whenever that implies row of f of x comma f of x dash is strictly less than epsilon. Okay, but in theorem we have given that sequence xn is a Cauchy sequence in capital is Cauchy sequence in X. By definition of Cauchy sequence, for given delta greater than 0, there exists a positive integer n such that d of xn comma xn is strictly less than delta for all n comma m is greater than or equal to capital N, by definition of Cauchy sequence. Suppose call this equation number 1 and this is equation number 2. Therefore, from 1 and 2 we get equation 2 says that d of xn comma xm is strictly less than delta for all n comma m is greater than or equal to n, and equation 1 says that d of xn comma xm is strictly less than delta, that implies row of f of x comma f of here is xn and xn. Rho of f of xn comma f of xn is strictly less than epsilon. So we get rho of f of xn comma f of xn is strictly less than epsilon for all n comma m is greater than or equal to capital N. So therefore sequence f of xn is a Cauchy sequence in 1. Okay. Hence proof of theorem is complete. Okay, we will stop here. Thank you.